Right, so in yesterday's lecture, we stopped at this slide. Okay, so we have learned on how to describe the molecular speed by using Maxwell-Boltzmann speed distribution curve. Okay, all right, so make sure that you know how to represent the Maxwell-Boltzmann distribution curve. So this curve is used to show the effect of temperature, okay, on the molecular speed, right? And also the effect of molar masses, okay, on the molecular speed. So as you can see, as the temperature increases, okay, from 100K to 700K, the molecular speed is also increases. Okay, the molecular speed of the molecule is also increases. So nampak dia punya graph tu, the curve is spreading out to the right ataupun to the more higher molecular speed for 700K. Okay, and the lowest would be 100K lah. Sorry, for 100K at temperature of 100K, okay, the speed is lower. Okay, the coverage of speed is lower for at 100K temperature. Okay, all right. So please make sure that you also represent the the number of molecule ataupun the luas bawah graf. Okay, dia punya luas bawah graf tu should be more or less macam the same. Okay, remember dia punya luas bawah graf tu, okay, sebenarnya sama, which represent the same number of molecule. Okay, so yang ni tinggi sikit, yang ni landai sikit, yang ni dia even landai. Okay, dia spreads out. So janganlah yang ni tinggi lepas tu yang ni kecil, macam dia tak comparable, okay, in terms of the number of molecule. So you kena represent it well, make sure that the luas bawah graf tu dia comparable, dia lebih kurang sama lah. Okay, cuma dia perbezaan bentuk of the curve. Okay, and then we have in terms of molar mass also the same. Okay, so the lighter the molar mass, by right, the molecular speed also increases. Okay, so helium, the molar mass is the lightest. So as you can see, okay, the curve spreads out to a higher molecular speed, which is more on the right hand side compared to chlorine. Chlorine dia berat kan, so berat that means the speed is not as fastest, okay, as fastest ataupun as high, okay, compared to helium dengan nitrogen. Okay, alright. So please take note that for the curve, okay, you should be starting at the same starting point. Nampak tak? This one. And also this one. Okay. It's just that the ending are different. Dia punya ending based on the effect of the temperature and also the effect of the mass. Okay. So lagi tinggi temperature, the higher the kinetic energy, the speed become faster. Therefore, the dia punya ending ni should be paling kanan, the most right of the x-axis. Okay, all right, moving on. Okay, so we have one checkpoint yesterday. So let's discuss this checkpoint first. Okay, the average velocity or mu RMS of an unknown molecule at 127 degrees Celsius is 600 meter per second. Calculate the mu RMS ataupun the speed at 1127 degrees Celsius. Okay, so it's the same gas but tested at 127 degrees Celsius and also tested at 1127 degrees Celsius. Okay, it's the same unknown molecule of gas. So to calculate mu RMS, okay, we can just use this formula, 3RT square root F over molar mass. Okay, all right. So when we want to calculate this at this temperature, the speed at this temperature, okay, we start at molar mass because we don't have this information. Betul tak? We have R, we have T, but we don't have the information on molar mass. Okay, so then we cannot calculate for the URMS. So we have to go back, kita tengok balik the question. So the information is given, okay, for this 127 degree Celsius. So for 127 degrees Celsius, we have the mu RMS. Like I said just now, it's actually the same gas. Dia adalah gas yang sama. So meaning that we can calculate the molar mass by using the mu RMS of this temperature. Okay, so mu RMS, this is at 127 degrees Celsius. Okay, by using the same formula 3RT over molar mass. Okay, but this time around we have this information. This is 600 meter per second. We have R, we have T. Make sure that you convert the T into Kelvin. Okay, and we can calculate for molar mass. Okay, all right. So this molar mass, make sure that the unit should be in kg per mole. Okay, so this molar mass later will be used in this formula to find the mu RMS at 1127 degree Celsius. Okay, all right. So you can start from the formula itself, and then from the formula itself, it will guide you on what to do next. Okay, bila kita start from the formula, bila kita nak masukkan the information, kita start dekat sini molar mass. So it tells us that, okay, kita kena find out the molar mass. Okay, cuba tengok the information from the question. Oh, dia bagi this one. So kita kena rewind sikit lah. Okay, we need to find the molar mass at this condition. Okay, because we know these two are the same. Sorry, dia adalah gas yang sama. It's just that they are performed at different temperature. The experiment is performed at different temperature. Okay, all right. Yeah, this is the working solution like I've shown to you just now. Okay, so you have to check, you have to calculate for the molar mass first. Okay, at 400 K. Make sure that you convert the temperature into Kelvin. Okay, once you have the molar mass, you can use this molar mass to find the mu RMS at 1400 Kelvin. So this is the mu RMS for this temperature. Okay, right, moving on. Next, we have Graham's laws and its application. Okay, so this is another law that you should know involving gases. Okay, all right, so make sure that you know to state, okay, make sure that you are able to state Graham's law and use it to calculate the rate of diffusion or effusion of gas. Okay, all right, so what is diffusion and what is effusion? Okay, so diffusion is a movement of gases from high concentration to low concentration. Okay, from a high concentration to a low concentration, meaning that the gas spreading of gases to occupy all the space available to them. Okay, look at the diagram here. Okay, so this is how we can represent diffusion. So on this side, we have a high concentration of gas, meaning that the particles are, we have a lot of particle gases in the in this side, okay, and on the other hand, this side we leave it empty, okay, and we have a divider, okay, to separate these two space. So this means this side has high concentration of gas particle. Okay, alright, this side low, ataupun in this case tak ada langsung kan, it's vacuum lah, tak ada langsung gas particle. Okay, just nak highlightkan from high to low. Okay, when we remove this barrier ataupun kita lift up the divider, okay, so the high concentration of gas particle just now will diffuse, okay, to a lower concentration of gas. So dia akan moving toward this side. So this process is what we call diffusion. Okay, it is a diffusion process. On the other hand, effusion is a movement of gases from high pressure to low pressure. Okay, so the molecule escape through a small hole into a vacuum. It's actually the same sebenarnya. Okay, on this side, nampak tak dia mention in terms of high pressure, but this one dekat diffusion dia mention in terms of concentration. Okay, tapi dia punya pemahaman, the understanding is still the same. You imagine, what do you mean by concentration? Okay, what is the relationship between concentration, high concentration and pressure? Kalau concentration of particles increase, concentration of particle is high, that means what is the correlation of concentration and pressure? High concentration means it will cause high pressure, because high concentration, the collision will be higher as well. Okay, so the higher the collision, the rate of collision become higher, therefore the pressure will also increase. Okay, which is the same as this one, from high pressure to low pressure, from high concentration to low concentration. But in terms of effusion, instead of using concentration, okay, it is mentioned in terms of pressure. Tapi dia punya pemahaman, dia punya understanding is still the same. Okay, alright, so dia punya significant difference between diffusion and effusion is in terms of the movement for effusion is through a small hole. Okay, they escape through a small hole. Kalau diffusion tadi, angkat je, dia bergerak terus. Okay, but this one dia tak angkat. It's just that the gas will move, okay, ataupun will pass through this small hole. Okay, so that is effusion. So pergerakan dia limited lah dekat situ. So dia kena keluar satu, okay, to this low pressure. Okay, to this low pressure side. So that is what we call effusion. Okay, make sure you know how to distinguish between these two, and then jangan confuse, because dia punya, it sounds almost the same, cuma dia punya beginning dia tu saja yang berbeza kan, so you may get confused lah. So please find a way for you to somehow bila diffuse, okay, you imagine diffuse ni boleh imagine like macam you spray minyak wangi kan, that is a diffusion process. Okay, you spray minyak wangi dekat sini, kata you spray minyak wangi closer to you because you nak bau tu kan, so it is you spray it closer to you. So this region, okay, we can consider it as having high concentration of the fragrance punya scent dekat situ. Okay, so after a while, okay, orang dekat belakang saya akan start to smell the scent. Dia akan start to bau scent tu. So the process of the fragrance, the scent to travel from this high concentration yang dekat dengan saya to that person yang belakang saya is what we call diffusion. Okay, and is what we call diffusion. So effusion adalah yang through hole. Okay, so dapat tahu diffusion, so effusion will be the one that through hole lah. Okay, yang melalui lubang kecil. Okay, so we have a formula to describe this diffusion and effusion, and it is known as Graham's law formula. Okay, so generally this law is used to compare the difference in rates, okay, between two different gases. When we talk about rates, it has something to do with time. Okay, rate has something to do with time. So dia ada function time dekat situ. So when the time is longer, the time taken is longer, so what happened to the rate? It is inversely proportional. Okay, macam speed. Speed kan, the distance over change in time. Change in distance over time. So speed is also what we call rate. Rate is the general term. Okay, it's the general term. So dia punya measurement tu, dia punya bawah ni mesti time. Okay, up here it can be anything. any kind of measurement. Okay, when it is over time, so that is what we call rate. The general term of it is rate. Cuma nama dia tu, it is called speed kalau kita guna distance over time. It is called weight loss kalau kita guna kg ataupun mass, this change in mass over time. Okay, and banyak lagi. Banyak lagi lah. Okay, as long as the over time, it is a rate. Okay, dia adalah type of rate. Okay, alright. So the law assume temperature and pressures are the same for the two gases. So kita fix the temperature and pressure. Okay, which varies in terms of rate, time, and also later molar mass. Okay, so by right, this temperature and pressure should be fixed to constant. Okay. Graham's law of diffusion and effusion states the rate of diffusion or effusion for a gas is inversely proportional to the square root of the molar mass. It is inversely proportional to the molar mass. Okay, so this is the formula for effusion and diffusion. So the rate is inversely proportional to the molar mass. Okay, lagi berat, okay, the heavier the mass ataupun the heavier the particles ataupun the substance ke whatsoever, by right the movement will be slower ataupun the speed will be slower. Okay, pergerakan dia akan jadi slow, and this cause the time taken to be longer. Sebab berat kan, so time taken will be longer for the particle to move ataupun to travel. And what happened to the rate? The rate will become, the value of the rate will become smaller lah. Dia punya value tu akan jadi kecil lah, rate dia tu. Okay, because it is inversely proportional. Okay, so rate 1 is inversely proportional to its molar mass. Rate 2, okay, is down here, therefore the molar mass should be up here. So square root of all the molar masses. Okay, alright, moving on. Gases with high molecular weight tend to diffuse more slowly than gases with low molecular weight. Like I mentioned just now, okay? All right, so this is the representation of diffusion. So imagine we have one side, we have gas A, and the other side we have gas B, okay? We have a barrier to separate these two gases, okay? All right, when we remove this barrier, they akan start diffusing with one another. It's just that now kita nak tahu which one diffuse better ataupun which one diffuse faster. It depends on the molar mass. Okay, so the heavier the molar mass, the slower the movement atau the slower it is to diffuse throughout the space. Okay, alright. So eventually dia akan mix lah. It's just that kita nak tahu kecepatan dia mix tu. Okay. Alright, okay, another example we have here. So in this bottle, we have ammonia gas, and then this bottle, we have HCl gas. As you can see, these two have different molar masses. Okay, so the mass for NH3 is 17 gram per mole. On the other hand, HCl has 36 gram per mole. Okay, which is HCl is twice of NH3. Dia punya mass dia twice of NH3. Berat lah dekat situ. Okay, so NH3 is lighter. Maksudnya dia akan diffuse from this bottle. Okay, it will diffuse faster compared to HCl. And then these two, when they mix ataupun when they react with one another, it will produce NH4Cl. Okay, and then from this experiment, we can observe that the NH4Cl from the fume here, okay, is observed to form ataupun appears on the HCl bottle. Apa maksudnya dekat situ? Menunjukkan that the NH3 dah diffuse faster. Dia dah diffuse dekat air ni, and then dia dah travel. Okay, so dia dah travel closer to the HCl bottle, and the moment HCl diffuse keluar saja, it will react with NH3 that is already there, dekat sini dah. Okay, so the moment dia react, it produce NH4Cl. So that is why the NH4Cl is observed nearer to HCl bottle. Okay, sebab dia move faster. Okay, diffuse faster. Okay, so the rate of effusion is the number of molecule passing through a porous barrier. So just now we are talking about diffusion, right? Okay, now we are talking about effusion. Okay, a number of molecule passing through a porous barrier. That means through a hole, okay, in a given time. The longer the time it takes, the slower is the rate. Therefore, the rate is inversely proportional to the time required for effusion. Sebab dia kena travel through hole, betul tak? So, dia kena travel through hole. So, dia kena ada, time is very significant dekat situ. Time is very important. Sebab tadi diffuse, dia tak ada hole ke tak ada apa. So, dia basically dia bergerak je lah, dia travels. Okay, but this time around, dia kena travel through holes. So, maksudnya dia kita nak tengok kecepatan dia travel through holes tu. So molar mass of course will play a role there, and we need to consider the time as well. Okay, for effusion kita kena consider the time. Okay, kesian dia nak travel through hole tu kan. So kita kena measure dia punya masa yang diperlukan untuk travel through the hole. Okay, so this is the initial just now, which is what we have for diffusion. Okay, so for effusion, we have to have this function of time function dekat sini. Okay, alright, so like I said just now, rate is inversely proportional to time. The longer the time taken, that means the rate will be reduced. Okay, rate akan jadi rendah lah, the value of rate will be slower lah. Bukan slower, dia punya value akan jadi rendah, tapi rate kita akan cakap slower. Okay, because time taken is longer. So please be careful guys. Okay, alright, so this one the opposite. Okay, it is inversely proportional. If we were to compare in terms of time dengan molar mass, they align. Okay, in terms of rate, they are inversely proportional. Okay, it depends on the question. If the question give out the information in terms of time dengan molar mass, then you should be using this part. Okay, kalau dia bagi rate and time, that means you have to use this formula instead of having molar mass in the formula. Depends on the question. Okay, apa question bagi information. Okay, like effusion rate at which a gas escapes through a pinhole into a vacuum. So we have red gas and blue gas. Okay, so kita nak measure dia punya rate to effuse through this pinhole. Okay, so that's why kita nak, so dia berebut-rebut lah nak tu. Kita imagine as if dia ada satu pintu kan, orang ramai nak keluar kan. So dia kena siapa yang lebih power in terms of lebih ringan, lebih laju, that means it will effuse faster to this low pressure site. Okay, right. Okay, so let's look at an example. Carbon and hydrogen is found to effuse through a porous barrier. Porous barrier, that means through a hole, a small hole in 1.5 minutes. Okay, alright, so carbon and hydrogen, this is a gas yang bukan carbon lain, hydrogen lain tau. It's an unknown gas. Kat sini kat bawah ni dia akan cakap unknown gas, which represent this carbon and hydrogen. It's just that we do not know how many carbon and how many hydrogen are present in the molecule. So we can assign it as X for carbon, okay, and hydrogen we can assign it as Y number of hydrogen. Okay, so this is the unknown. So this unknown gas travel through a porous barrier, okay, and requires only 1.5 minutes of time. Okay, under the same condition of temperature and pressure, it takes an equal volume of bromine vapor, okay, 4.73 minutes to effuse through the same barrier, which is longer than the unknown gas just now. Okay, the same condition, the same volume, but the time taken is longer for bromine gas. Okay, so bromine gas, we know the molar mass of this gas. Okay, later we can compare. So you have to calculate the molar mass of the unknown gas and identify. You have to identify the gas, this one. Okay, all right. So how do we solve for this? Okay, so this is the representation of the experiment lah. Okay. All right. So the molar mass of bromine is 159.8. Okay. So this is the formula. Okay. The formula, because we are talking about effusion, right? Okay. So since the information is given in terms of time dengan molar mass sahaja, we don't have any information on the rate. So that's why kita hanya guna this part sahaja. Okay. All right. So 1.5 is for the unknown and 4.73 is for the bromine. Okay, so the molar mass of the unknown gas is to be determined. Okay, kita pun solve for it and we have this molar mass of the unknown gas. Okay, alright, so this is the molar mass of the unknown gas. Next question, you have to determine the gas. Okay, you have to determine the identity of the gas. Alright, so how do we determine that? So kita kena determine, we know that the gas consists of carbon and hydrogen, but we do not know the chemical formula of the gas. Okay, alright, so we use this information, the molar mass of this gas, to guide us on how to determine the identity of the gas. Okay, alright, so imagine if we have one carbon, kita boleh try and error lah. Okay, if we have one carbon, which is already 12 gram, dah 12 gram dah ada kat situ. Kalau kita ada dua carbon, okay, imagine if we have two carbon, that means the molar mass will be 24 and above something lah. Okay, it will be more than 24. But the molar mass that we have here is 16.1, which is less than 24. So obviously, there's only one carbon in the molecule. Okay, alright, so after all, dia ada carbon dengan hydrogen kan. So kalau there's only one carbon, so the rest will be all hydrogen lah. So we have 4 hydrogen. So 16.1 minus 12. Okay, kita akan dapat 4.1. Macam tu. So 4.1, so hydrogen is 1 gram kan. So if 4 gram, that means we have 4 hydrogen. 4 hydrogen atoms that is attached to the carbon. So from there, kita boleh determine lah the identity of the gas. So the gas is a methane gas or CH4. Okay, alright, so you can predict from the molar mass. So the molar mass is our reference ataupun our guide in order to determine the identity of the gas, the unknown gas. Okay, right, moving on, we have another example, a mixture of helium and methane, okay, is placed and is in an effusion apparatus. Calculate the ratio of their effusion rates. Okay, alright, so the given information is in terms of dia nak macam tak bagi apa-apa kan, but dia bagi sebenarnya helium, because these two are known gases. Known gases meaning that the molar mass should be known lah. Kita tahulah the molar mass. Okay, alright, dia molar mass is given, assume dia bagilah. Okay, so the ratio of their effusion rate. Ratio maksudnya atas dan bawah, S dengan Y. So this is what we call ratio. Okay, alright, so dia nak ratio of rate. So this one. Okay, alright, so we have the molar mass. So we want to find this ratio. Okay, alright, so when we solve for this one, kita solve molar mass, kita insert the values, and then we solve for it, so we got 2. Okay, so the rate of helium, the ratio of rate helium over rate CH4 is equal to 2. Okay, so itu maksud ratio. Right, moving on. Okay, we have how many? Okay, we have 2 checkpoints. Okay, please complete question 1 first. Okay, I give you 3 minutes. Ditunjuk kat jawapan. Please complete this checkpoint. Okay, we will discuss it after 3 minutes. Okay. Okay, all right. Are you done, guys?
Yes.
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 All right.
Yes.
So panas laptop saya ni. Kerja keras ni laptop ni. Okay. All right, so let's go through the question first. A sample of unknown gas effuses in 10 minutes and equal volume of H2 in same apparatus under same condition effuses in 2.42 minutes. Calculate the molar mass of unknown gas. Alah, macam lebih kurang sama je soalan dia kan. Okay. Alright, so so the information are given in terms of time and also molar mass. Right? So we have the information on hydrogen. So that is considered as molar mass lah. Okay, all right. So we're going to be using this one. We don't use this red part. Okay, we use this part. All right. So kita masukkan all the information and so you can straight away calculate the final molar mass. Right? Okay, so this is the molar mass of the unknown. Right, so we have one more question. Okay, so this will be your homework, right? So we will discuss it next week. So I'm going to proceed to our next subtopic, which is deviation from ideal behavior. Okay, all right. So learning outcome, make sure that you are able to explain quantitatively the deviation from ideal behavior at high pressure and low temperature. And then make sure that you know how to use Van der Waals equation to solve quantitative problems. Okay, all right, so the title itself, real gases deviation from ideal behavior. So initially, okay, we have real gases behave as ideal gas. So ideal behavior, what are the two ideal behavior ataupun condition that we can assume the gas to be ideal gas? Condition dia apa? Ataupun behavior dia apa?
Repulsion.
Yes, those two please ingat Alright, so we have no attraction or repulsion between the molecules, and then the particle gases do not have volume. The gas do not have particle volume. It's more on the particle volume lah. Bila dia cakap volume tu, dia boleh jadi volume of container, volume of the particles kan. We are talking about particles volume. Okay, alright. So, deviation from ideal behavior adalah moment di mana real gas tu dia dah tak follow ideal. Dia dah disobey ideal. Maksudnya dia patutnya there's no attraction, dia start to experience the attraction among them. Okay, and then patutnya there's no the particle volume is negligible. Okay, now dia dah start ada its own particle volume. Okay, alright. So the question now, when these real gases start to deviate from ideal behavior. Ada dekat learning outcome ni, dia dah cakap at high pressure and low temperature. So later we will look into this, on how at high pressure and low temperature, the real gas ataupun the gas itself deviate from the ideal behavior. Okay, alright. So bila dah deviate from ideal behavior, for the PV and RT, so this is the equation for the ideal gas. Okay, alright. So bila dia deviate, supposedly we cannot use this PV and RT. Okay, we have to modify this formula, and we have a formula to describe the real gas that is known as Van der Waals equation. Okay, so that is why you should know these two lah. Okay, moving on. Amboi, punya banyaknya benda dekat dalam this one slide. Okay. Recap for the ideal behavior. The ideal gas model makes two assumptions. So the gas has negligible forces between its constituent. That means no interparticle interaction. Okay. It's either repulsion ke, attraction ke, regardless. Okay, that's why dia cakap interparticle interaction. The interaction can be in terms of attraction or repulsion. Okay, alright, so there's no forces, there's no interaction between the molecule. Secondly, gas molecule ataupun gas atom have negligible volume, particle volume sebenarnya. Okay, so it has particle volume. It's just that it is too small that it can be neglected. Ini pun sebenarnya ada. It's just that dia not significant and it can be neglected. Ideal gas ni senang ya, dia abaikan je. Okay, sebenarnya kalau real gas betul-betul, dia ada forces tu. It's just that dia tak dominant. Ideal gas senang je. Tak dominant, abaikan. Okay, so itu ideal gas behavior. Alright, so zero volume of gas particle. Okay, for real gas maksudnya yang sebenar lah, supposedly dia ada that forces kan. So cuma dia diabaikan saja. So real gas is a gas that does not behave as an ideal gas due to interaction between gas molecule. So we can say that this is the deviation. Okay, this is the deviation from ideal behavior. And this deviation occur at very high pressure and low temperature. Okay, so these are the two conditions where the real gas yang normally would obey the ideal behavior, dia dah disobey. Dia dah tak follow the ideal behavior. Okay, at these two conditions. So please take note that you should know bilakah gas ataupun real gas behave sebagai ideal behavior atau behave sebagai ideal gas. Dia mesti opposite to this one. Okay, opposite to this one. So dia jadi ideal behavior, ideal gas when at low pressure, secondly high temperature. Okay, dia mesti opposite to these two lah. Okay, okay. Nanti kalau soalan keluar, make sure you baca betul-betul dia nak ketika dia behave sebagai ideal ke ataupun dia deviate from ideal atau to behave like real gas. Okay, so please baca betul-betul, you kena tahu. And then the reason kenapa at lower pressure and high temperature dia behave sebagai ideal gas. Okay, remember cerita yang kenapa at low pressure means space dia besar. Bila space dia besar, okay, dia makin jauh from one another kan. So bila makin jauh, that's why interparticle attraction tu, there's no interparticle attraction. Bukan no. The interparticle attraction is negligible. Same goes to at high temperature. Kenapa at high temperature they behave as ideal gas? Sebab at high temperature dia ada extra energy, high kinetic energy. So the speed become faster. So they tend to move faster. Bila tend to move faster, dia tak sempat nak interact with one another tau. Tak ada intermolecular forces dekat situ. Okay, dia tak ada experience any attraction there. So that is why at high temperature they behave almost ideally dengan dekat lower pressure. Okay, so the opposite to that, dia deviate from ideal gas behavior. Okay, alright. So kenapa at high pressure dia deviate? Because the distance between particle is too small and the molecules are too crowded together. So look at this diagram here. Okay, imagine this is a piston. Okay, high pressure means high external pressure. We are talking about external pressure. Okay, remember pressure, we have two types of pressure. It can be external and also internal. Okay, condition yang kita mention dekat sini is the external pressure. Okay, kita yang buatkan dia supaya the pressure become high. Okay, alright. So the reason kita kata the pressure, dia punya pressure tinggi adalah when we compress. Imagine we compress the piston, kita push down the piston. So what will happen? The space between them become become decrease. Okay, reduce. Okay, so it becomes smaller lah. The space becomes smaller. Okay, and then the number of molecules still maintain. Tadi banyak ni, after decompress pun still banyak ni. Okay, right. So one thing yang kita kena take note adalah bila they come closer to one another, okay, they start to experience interparticle attraction ataupun interaction. Okay, they start to interact ataupun ada attraction ataupun repulsion. Okay, doesn't matter. Both of them we call it as interaction lah. Okay, so they start to feel that. Faham tak? So that is why bila begitu dia dah disobey the ideal gas sebab dia dah start to feel the interaction. Okay, that is for high external pressure. Okay, when we compress further kan, bila kita compress further, dia dah start to feel the interaction between them. Okay, when we talk about internal pressure, okay, when we talk about internal pressure last time, ingat tak yang Boyle's law tak silap saya? Okay, bila kita compress, okay, kita imagine dia adalah ideal gas kan, kita assume the internal pressure will also increase. Sebab apa? The space is now smaller. Space smaller, so dia akan collide more, betul tak? Dia collide more dekat tempat yang sama among themselves. So that is, those will produce pressure. Okay, that's why for ideal gas, kita expect that bila dia compress, pressure dia tinggi, okay, the pressure will still be higher. Okay, will still be higher. Sebab apa? Because kita neglect the intermolecular forces between them. Okay? Tapi sebenarnya bila kita compress, the pressure, okay, is not as high kalau kita imagine dia untuk ideal gas. Sebab ada effect of interparticle interaction. So bila dia dah start interact, mungkin dia dah start combine. So bila dia start combine, okay, dia dah ada forces form between them. So they start to dia dah jadi besar kat situ. Bila dia interact, dia melekat lah kan. So dia interact, dia jadi bulky, besar, okay, dia jadi berat. So what happen in terms of speed kat situ? Speed jadi slower. Bila dia collide with the wall of the container, will it be as impactful kalau compared to if kita assume there's no forces between them? No. Okay, dia tak jadi impactful lah. Dia jadi the collision will be not as impactful. So the pressure will be lowered. The internal pressure will be lowered. Okay, sebenarnya cuma yang awal-awal tu kita abaikan. There's no intermolecular forces. But this time around, sebenarnya bila dia come closer, dia betul-betul rapat tu, dia dah start. Dia bukan dah start, dia dah rasa the intermolecular forces. So sebenarnya P real should be less than the P ideal. Okay, P real should be less than the P ideal. Ni saya nak bagi overview dekat awak sebab later kita akan ulang balik slide-slide kemudian tu ada lagi. So kita repeat banyak kali so that you have the idea of it. The more you expose yourself to the same information, the more you absorb. Okay, so that's why you kena dengar banyak kali. Right, so that's the reason why sebenarnya realitinya, okay, the internal pressure is lower than what we expect for ideal gas. Ideal gas sebab kita abaikan the forces. Okay, that's why lah kita boleh kata, oh dia punya by right dia punya pressure will be higher. Okay, sebab kita abaikan the forces. So kalau kita tak abaikan, sebenarnya dia rendah. Okay, but logically speaking, because they come closer to one another. Right. Secondly, at low temperature. Okay, ni logik je. You boleh nampak, you boleh imagine ni. Ni bukan something yang susahnya nak imagine macam quantum ke apa kan. Ni memang dia very straightforward. Okay, alright. Why is it at low temperature the real gas deviate from ideal behavior? Okay, kenapa? Alright. At low temperature, that means become colder lah. Okay, dia become sejuk ataupun tak payah cerita in terms of that lah. Okay, at low temperature, let's talk about kinetic energy. At low temperature means the kinetic energy is lower. Betul tak? The kinetic energy is lower. That means the movement, the kinetic energy is related to the speed, the movement of the gas particle. Okay, so the movement of the gas particle will be slower. Dia bergerak slower lah. Okay, okay, bila dia bergerak slower, ni macam ni dia bergerak. Okay, and then bila dia come closer to one another, they have enough time to interact. Sebab apa? Dia punya speed tadi dah slow. Slow sempatlah, hey apa khabar? Sihat? Dia ada that moment to interact with one another. Compared to kalau high temperature tu, dia zoom. Amboi, sombong kan? Because of the speed dekat situ. So low temperature cause the speed of the molecule to slow down and they have time to interact. Bila dia interact, and mungkin dia akan combine, okay, dia ada interaction dekat situ and the same effect. Okay, we have for high pressure just now, kita ada for low temperature. Okay, bila dia dah interact, that means dia akan collide, collision, dia punya speed will become smaller, slower. So dia punya, bila dia berlanggar pun dia become slow. Okay, dia tak impactful at low temperature. Okay, alright. So under both of these condition, kalau kita combine these two condition at high pressure and low temperature, the volume of particle becomes significant, thus all gases can be liquefied. Okay, one more thing lupa saya nak cakap. Okay, imagine bila you push down the piston ataupun you compress down, okay, you increase further the external pressure, you push kat bawah tu kan. Not only dia punya free space dah berkurang kan, dia free space dah berkurang, so they come closer to one another, so dia dah jadi makin rapat. Bila dia jadi makin rapat, they start to have its own volume. Nampak tak? Tadi dia tak ada volume sebab dia punya space between them are far apart. Now they come closer to one another, okay, and they start to have their own volume. Dia dah start ada volume. Tadi kan kita abaikan, now dia dah ada its own volume. Okay, so that's why the volume of the particles, the volume of the particle here becomes significant, thus all gases can be liquefied. Kalau you compress even further, you akan dapat liquid. That is what happen untuk kita punya reset yang sembuh nyamuk tu kan. You goncang kan, you dengar macam liquid kan. Tapi once you release the gas, okay, dia akan jadi gas. Sebab apa? Sebab volume dah jadi sangat besar. Dekat dalam tu dia compress gas. So space dah jadi kecil. That's why kita boleh dengar dia macam liquid. Dalam tu. That's why kita panggil compressed gas. Okay? Sebab the volume is now very significant. Bila you compress further, dia boleh jadi liquid. Okay? Alright. Okay. Kau apa tadi? 2 minit. Okay, 2 minit. Alright. Okay, so we can also represent this behavior at high pressure and low temperature using graph. Okay, alright. So this is pressure, this is temperature. Alright. Nampak tak? We have a red line dengan a green line dekat sini. Kita ada red dengan line. Red dengan green. Red represent the ideal gas. Argon is the real gas. Example adalah argon. Okay, alright. Nampak tak? At lower pressure, kawasan lower pressure, dia punya tu nampak as if dia overlap with one another. Kan? So maksudnya kita boleh kata real gas, which in this case argon, okay, real gas at lower pressure has behave as ideal gas. Okay, tapi when we increase the pressure further, nampak tak dia deviate? Nampak tak dia deviate? So maksudnya menunjukkan at higher pressure, the argon start to deviate from ideal gas. Dia dah tak jadi overlap dah. Makin lama tak overlap, dia dah terpisah. Okay, this is what we call deviation. Same goes to temperature. At very low temperature, nampak tak? This one, very low temperature. Okay, this is temperature. Okay, low temperature they start to the xenon start to deviate from the ideal gas punya line. Kalau high temperature, they still overlap with one another. Okay, they macam combine. So they behave. We can say that xenon behave almost ideally at higher temperature. Tapi lower temperature, okay, it start to deviate. Okay, alright. So ni pun sama. Okay, we boleh nampak dekat situ. So this is the ideal gas. Yang merah ni ideal gas. Nampak tak? Ada yang ke atas, ada yang ke bawah, ada bawah lepas tu naik atas, lepas tu bawah sikit naik atas. This is what we call deviation. Yang dia sama dekat kawasan ni. Dekat sini. Ini yang dia behave sebagai ideal gas. So the moment the temperature ataupun the pressure is altered, dia akan deviate. Cara deviate tu dia pun ada efek juga. Yang kalau ke bawah ni, apa yang lebih dominant? Mungkin efek size of the intermolecular forces, macam H2O dah start ada hydrogen bonding which is stronger compared to dipole-dipole forces. Those ada effect on this intermolecular attraction. That's why you akan nampak dia punya yang ni ke bawah, yang ni yang ni atas sikit, lepas tu naik atas. Dia different in terms of the curve itself. Okay, alright. So let's stop here. Okay, so we have one checkpoint. So we will discuss this again during next week's lecture. Okay, alright. So that is all for today. Okay, everyone. Okay, thank you. Kalau ada soalan, postpone during tutorial ataupun next week. Okay, alright. So thank you everyone.
Madam,
yeah.
Boleh tak tengok checkpoint 13 question 2 sebab tak ada dekat slide.
Ya ke? Checkpoint 13. This one. Okay, snap. Okay.
Tak ada, madam tak ada share screen kah?
Ya. Aduh. Lambat kejap. Alright, this one. Okay. Alright. Okay dah. Jom. Dah lambat awak ni. Kan ada kelas ni. Okay, bye-bye. See you.
Thank you, madam.
Madam.
Madam.